Hello, and thank you for joining us for this exclusive webinar on how to design high-speed motors using multi-physics simulations. Infolytica Corporation is the first and only software company still dedicated to electromagnetics. It's not only the core of our expertise, it's the core of so many design and analysis problems, even when talking about multi-physics, especially motors. We took our expertise in general electromagnetics and consulted with several well-known motor designers to create MotorSolve, a product completely written with theirs and your needs in mind. Adrian's presentation will focus on understanding why virtual prototyping with simulation software is a must-have tool for motor design engineers, exploring how multi-physics considerations impact the optimum motor design, and how MotorSolve can be used to virtually prototype and replicate a variety of physical laboratory experiments for motors. Feel free to submit questions at any time. After his presentation, Adrian will answer as many questions as time allows. If we missed your question or run out of time, we'll be providing a document very shortly after today's presentation with answers for you. Now I will let Adrian take this presentation over. Adrian?
Good afternoon, ladies and gentlemen. Our webinar this afternoon is going to be discussing how to design high-speed motors using multi-physics simulation. We have a particular design in question. It's a brushless permanent magnet 3-phase motor. This motor must deliver 20 millinewton meters at 20,000 RPM. It must do this at a 100% duty cycle for at least 1 hour steady state operation. We've imposed some physical limitations on our design in question so that we had a framework to work with. And specifically, we have given ourselves a 25 millimeter overall outer diameter for the housing. We also have incorporated a 1 millimeter thickness for the housing, which gives us a 23 millimeter outer diameter maximum for the stator lamination. With regards to the length along the shaft, we have stipulated and confined ourselves to a 25 millimeter overall length with 1 millimeter thick end plates that gives us a 23 millimeter overall active region. We're also assuming that we'll have 5 millimeter end winding extents on both sides with a little bit over a millimeter in clearance. This results in a stack length of 10 millimeters. And with our choice of 5 millimeters for the diameter of the shaft, we've got a pretty good example of what we're going to use with respect to the package size. Additionally, we're going to confine ourselves to a magnetic air gap of a 0.5 millimeter. And because we're going to be operating at 20,000 RPM, we're going to also then contain the rotor in a non-magnetic shell. And this shell has a 1/4 millimeter thickness. This gives us an overall air gap, physical air gap of a 1/4 millimeter. We've gone ahead and also picked from and chosen a series of materials for our components. For our stator winding, all of the winding will be American gauge round copper wire. Our stator lamination is going to be made of a cobalt iron alloy. This might be a Hyperco material from Carpenter or perhaps a Vacador from Vacuum Schmelz. The magnets are going to be a neodymium iron boron class of magnet, and we've chosen a 48 megagauss Ørsted grade to give us the best flux density potential. Our back iron is going to be cold rolled steel. Our rotor sleeve is actually made of a carbon peak weave. The shaft will be made out of 304 stainless. Our housing and end plates will be made of aluminum. And any epoxy that we choose to use is going to be of the highest grade epoxy with respect to the thermal conductivity. And I've shown here the overall value of 0.176 watts per meter per degree C. Now, there are a wide range of possibilities for our topology, and we've confined ourselves in this exploration of design to the surface-mounted permanent magnet rotor topology. And we've chosen to look at a series of different pole counts. We're going to go from 4 to 6 to 8 up to 12, and a variety of stator slot pole counts from 9 to 12 and up to 36. This gives us a total of 50 different machine combinations. Now, as Chad has described, we couldn't possibly go ahead and make all of these 50 machines with a variety of perturbations and such on the component configuration. So we're going to virtually prototype those. And we're going to virtually prototype those with the software called MotorSolve. And it's important to note that the magnetic performance that we'll be assessing utilizes a 2D magnetic finite element method. And any thermal results that we show, or the performance of the machine, will be a result of 3D thermal finite elements. Now, we're going to go and assess those 50 different machines, and we're going to do that by looking at the balance of the layout first. And we're going to utilize MotorSolve's stator winding interface. It looks like this. And it's got a series of different panels and such that give you information about the winding based on geometry and such, but we're going to concentrate on this area here on the middle left. And I've underscored a couple of examples for you. On the top left, you can see here that the software has determined that there is an automatic layout that's possible, which gives us a balanced winding. Furthermore, on the bottom right here, I have an additional layout which clearly states that we couldn't find a valid layout for a balanced winding. So utilizing this technology, I summarized the result of my 50 experiments here in the table. And you can see here that there are several which I've marked with an X, which could not determine a balanced winding. There are several machines which were able to create a balanced winding. And to put our best foot forward, I have decided to choose to use those that had 100% balanced winding in our configuration. And you can see here that that means we have a 4-pole 12 slot, a 6-pole 18 slot, an 8-pole 24 slot, a 10-pole 30 slot, and our final configuration series, a 12-pole 36 slot. Now, there's a wide range of possibilities for how we would balance everything inside of the motor. But to simplify things, I have chosen to explore 4 different rotor diameters. It's going to choose 10, 11, 12, and 13 millimeter diameter for the rotor. With our 5 configuration, that means that we have a total of 20 machine designs to review. So we're going to go and look at a variety of different responses based on how we configure the following parameters for the rotor. You see here that we're going to modify and change the width of the magnet and the thickness of the magnet. Here would be my thickness. Here would be my width. Additionally, we're going to change 4 parameters for the stator. We're going to change the slot depth, slot opening, tooth tip thickness, and the tooth width. Here I have my slot opening, my tooth tip thickness, my slot depth, and my tooth thickness, or tooth width. Now, as we assess these machines, our first series of assessments is actually going to be a 3-tiered approach. And we're going to look at the winding. We're going to try and put as many turns of copper wire as we can into it. We're going to try and balance that with regard to the current density and monitor my slot fill. All of that while trying to deliver the required torque and keeping the flux density levels at a level which is tolerable. So with regards to my first tier of the machine performance criteria, we're going to put a series of turns inside the slot. We're going to vary the wire gauge in half gauge increments, monitor the slot fill so that it never goes above 45%, and monitor the current density such that we can get a reasonable alternative for the machine. And we're going to use MotorSolve's stator winding interface to help us with this. So here you can see I've zoomed into the wire diameter parameter, the number of turns parameter, and the resulting slot fill associated with a given design. Our second tier is associated with the fact that we need to generate 20 millinewton meters at 20,000 RPM. And so we're going to utilize an experiment within MotorSolve that allows us to do this. And just for a quick digression, I'm going to reference the fact that we're going to utilize 7 overall experiments in MotorSolve to help us with assessing this machine. We're going to use the Cogging torque, the back EMF, the torque speed, the efficiency map, the temperature curve, the motion analysis, and the thermal fields. All of those are going to be part of our assessment. Returning to our machine response, we're going to utilize MotorSolve's motion analysis experiment to develop and create a series of values for torque for those designs. And we're going to compare and see if we deliver the 20 millinewton meters or not. Our third tier of assessment is going to be with regards to the flux density. And we're going to scrutinize that flux density in 3 places: the lamination teeth, the lamination back iron, and the rotor back iron. And in all 3 of those places, we're going to scrutinize such that the flux density does not go above 2 Tesla or 20,000 gauss. To do this, we're going to run another experiment within MotorSolve. It's called the instantaneous fields experiment, and it gives us direct access to the flux densities throughout the entire machine. Here's a representative example. You can see here on the bottom legend that I'm going from 0 to 2 Tesla. You can see as I look around the machine that, especially in the rotor here, there's no flux densities in danger of going to 2 Tesla. As I review the flux in the back iron, it too is consistent with nothing that's going to go near 2 Tesla. I think the peak here is about 1.6 Tesla in orange. There is a couple of red spoke of the lamination, which have a orange, deep orange color. The flux densities in those regions are about 1.9 Tesla, and so I have ensured that the flux densities do not exceed 2 Tesla in this example. Furthermore, we can zoom in and get an idea of the detail of the flux density in the teeth, in the air gap, wherever we desire. This is just a representative example. So we've gone ahead and we've made a wide range of perturbations on those 6 parameters for the rotor, 2 for the rotor and 4 for the stator. And then we've explored each of these 3 experiments, and we've come up with the following table, which shows us the possible designs and those that are passing. And it is instructive to note that with the 4-pole 12-slot series, none of the possible 4 configurations passes our stringent criteria. With the 6-pole 18-slot, we have 3 machine possibilities which pass. For the 8-pole 24, all of the configurations pass, same as with the 10 and the 30 slot. And with our 12-pole 36 slot, we have 2 machine types, the 11 and 12 millimeter OD, which pass. So with our 3-tiered approach, we have gone and taken our initial 20 designs and whittled it down to 13 possible candidates for our Optimum. We're going to embark upon another test or experimental result, which is the Cogging torque test. And with our cogging torque test, we're going to define a success to be a cogging torque that is less than 5% of the rated torque, or in other words, 1 millinewton meter or less. To assess our machines, we're going to use another experiment within MotorSolve called the cogging torque test. A result of that test may look like this. It gives you a full period in the rotation of the machine. And you can see here that this example has nearly 2 millinewton meters of torque for the cogging torque, and this would be a failing design because it's well above our maximum of 1. Again, if I show you a summary table which shows the designs which pass, turns out that none of the 6-pole 18-slot series pass. None of the 12-pole 36-slot machines pass. I have 2 machines that pass in my 824 series and 1 that passes in my 1030 series. We have an additional phase or tier of our criteria that we're going to assess, and that is we're going to assess the back EMF constant. And each of the machines that we're going to use as a possible candidate has got to deliver at least 1 volt per 1,000 RPM. To assess this performance, we're going to utilize another experiment, the MotorSolve back EMF experiment. A typical outcome would look something like this. And again, I have a table of summary which shows that of my 3 finalists and the candidates here, all 3 of them pass. It's interesting to note, and it's probably not a surprise, that they all passed due to the fact that they all also generated appropriate torque. To help us further scrutinize the designs, we're adding an additional criteria, and that is that the waveform for the back EMF cannot have significant higher order harmonics. And by definition, I've declared that the harmonics above the 7th must have amplitudes less than 1% of the fundamental. Here I have a reference for a back EMF, which would be a failed design, because as we look at this design, or this voltage for the design, we see that it actually has some significant higher order harmonics. In fact, the 37th harmonic has an amplitude which is nearly 5% of the fundamental. So if I look at and assess the possibilities for the passing of the designs, turns out then that my 10-pole 30-slot configuration falls out and is no longer a candidate, and I end up with 2 possible candidates, both in the 8-pole 24-slot series, my 10 millimeter and my 11 millimeter OD candidates. So now, just as a summary, I want to make it clear that we have created a multifaceted filtration of the design criteria for this motor. And the passing candidates have a slot fill less than 45%. The current density is less than 8 amps per square millimeter. The torque is delivered at 20 millinewton meter at 20,000 RPM. All flux densities are less than 2 Tesla. Both cogging torques are less than 1 millinewton meter. Both deliver a back EMF of at least 1 volt per 1,000 RPM, and neither of them have any substantial higher order harmonics. So we're forced with the task of comparing the final 2 candidates and coming up with a winner. And the reality is, if we look at the criteria for all of the performance, we see that they're basically the same, except for when we look at the cogging torque. And the cogging torque for the 10 millimeter rotor ID is less than half of that for the 11 millimeter. fact, it's about 45%. You can see the peak values. For the 10 millimeter, it was 0.43 millinewton meters. And for the 11 millimeter, it was 0.94 millinewton meter. So our clear winner is the 8-pole 24-slot motor with a 10 millimeter rotor OD. So now we need to know what that really means. From a physical perspective, the way that it maps out in the geometry is that the magnet thickness is 1.25 millimeter. The magnet width is 2.6 millimeters. With regard to my stator, the slot depth is 5.55 millimeters. The slot opening is 1/4 millimeter. The tooth tip thickness is 0.2 millimeters. The tooth width itself is 0.595 millimeters. With this configuration, I can put 16 turns of number 26.5 wire gauge in it, and we have a slot fill of roughly 44.98%, and we satisfy all of the criteria that we need to move forward. Now further, what does this mean from the standpoint of the physicality of the machine? Well, I'm showing here the masses, and the total mass of the machine is under 50 grams. You can see the various masses. The rotor total is about 11 grams. The stator total is about 30. My housing is just under 10, and the total is just under 50 grams. Now, to give us comfort as we assess things, here's our Cogging torque profile for this winter. You see the peak torque of 0.43 millinewton meters. Our back EMF constant for this machine is 1.165 volts per 1,000 RPM. And indeed, there are no higher order harmonics in the waveform. Further, we are going to run an additional test to help us scrutinize the machine over the full speed reference. And so we're going to run a torque speed curve. And here we have a resultant curve indicating that we have our 20 millinewton meters, the entire range up beyond our 20,000 RPM. We're going to run an additional test to help us assess things, and so we're going to run an efficiency map experiment. And here is our result for the machine. And then utilizing the motion analysis test that we've run before, we're also now going to look a little bit more in detail in the overall machine response. So you can see here at the top that we met our 20 millinewton meters of torque. Our efficiency is 92.6%. Our wire or current density is under 8 amps per square millimeter. And I've got a distribution of losses associated with things from the winding to the teeth and such. As a summary, you can see here that we have a little bit over 45 watts of input power, 42 watts of output power with the efficiency of 92.6%. The drive frequency is a little over 1,300 hertz. The breakdown of our losses is such that we have 3 3/8 total, 1.85 in the winding itself, a little bit over 1.5 in the stator lamination. There are losses in the rotor back iron and magnet, but these are sufficiently less than the other candidate pieces. So because of the air gap, they're not significant in the result of the physics. And now we need to do our multi-physics considerations. What happens to this motor when it's driven with 100% duty cycle for that 1 hour test of steady state operation? How does the generated heat from the components impact their material properties, and do we in fact still meet the requirements? So we're going to assess the machine response with an additional experiment. It's called the temperature experiment. it allows us to review and get a thermal response as a function of time for each of the components in the machine. So this is a representative example. I've run the test for 60 minutes. Because of the nature of the number of components, I've chosen to pick 2 of them to depict in the graph. But you can see here that both components, the winding, has stabilized to a temperature of just under 85 degrees C. The magnet is stabilized to a temperature just under 70 degrees C. And we can use this information to go back to our magnetic simulation with a coupled reference for the components, and we can rerun this motion analysis to look and see where we actually reside at steady state or at temperature. And lo and behold, the performance is now under desired specification. We have less than 20 millinewton meter of torque, and so our criteria is not satisfied. And we can look at that through our torque speed curve and again verify that we're just under throughout the entire range. And so we need to make an adjustment of things because we no longer meet requirement. So because the torque is too low, we're going to adjust the initial current to see if we can improve it enough to give us and meet requirements at steady state. So we're going to try a new currents value. We originally started with 0.83 amperes. We're going to move up to 0.89 amperes. That's a 7% change. And we're going to assess things at 20 degrees C. We see here that we have a little over 20. We have 21.5, in fact, millinewton meters. We have still maintained our under 8 amp per square millimeter constraint. We've got additional losses. We're going 3.66 instead of the 3 3/8. And so we are going to generate more heat, but this time we're going to see if we can actually meet spec. Here is our 20 degrees C torque speed curve. We're able to generate that throughout the entire range of speed. At this point, we're going to run another temperature experiment with our new configuration for current. Here's the result. The winding is now stabilized at 95.6 degrees C, the magnet at 77.3. For the winding, that's an 11-degree increase. For the magnet, that's an 8-degree increase. But note that the temperatures have stabilized. Well, in order to give ourselves some comfort in the design and how things have progressed with respect to temperature, we're going to run another experiment and look at things a little bit more closely. So we're going to run what's called a thermal field simulation, and we're actually going to look at the distribution of the temperatures on the components. So here I have shown a temperature shade plot at time t equals 0, where we're at ambient temperature. Everything's at 20 degrees. You can see here that I'm plotting from 20 to 100 degrees C. If I progress through, I'm going to actually progress through from 0 to 60 minutes in 5-minute increments to show the progression of the temperatures. So the next one is at 5 minutes. You can see here the progression in the temperature. The stator components are now into the low 40s. If I move on to my 10-minute, 15, now the stator's up into the 70s. My rotor components are down into the low 50s, let's say. We keep on progressing through, and you can see the shapes of the contours on the components change as a function of their temperature. And here you can actually see a bit of red in my stator area as we approach getting into stable state. And as we near the 60-minute point, we've reached stable state or steady state. And we can see the distribution associated with what we had in our graph. So we see here that the winding is in the middle 90s. The rotor is in the middle to upper 70s in temperature. And it gives us confidence that we have a good distribution associated with our temperatures. Now if we run a motion analysis to get an idea of what the response of the machine is at the temperatures at a steady state, we see here that we now actually do meet spec. We're a little bit over 20 millinewton meters at temperature. Our efficiency has dropped a little bit, but it's still over 90. We're at 91.1. We can verify again that the current density in the conductors is appropriate and less than 8 amps per square millimeter. And if we go and we look at the remaining kinds of performance criteria, here we can see the torque speed curve, and we see that we have our 20 millinewton meters all the way through the range of 20,000 RPM. We can look at our efficiency map and get a feel for how and what efficiency we would have under every operating condition to maintain and get that 20 millinewton meters at each speed. We can also look at the back EMF and clarify that it is reduced, and it's about 7% low compared to the previous value at 20 degrees C. And at this point, we're going to explore a couple of final machine details associated with where we may be vulnerable with regards to the temperature and the response of the machine. So at this point, we're going to run an additional experiment. We're going to go back to the instantaneous fields experiment and look at the distribution of flux density specifically in the magnets. And we're going to compare what it looks like at 20 degrees C, which is the ambient, and then at the operating temperature of 77 degrees C. So here's the flux density plot, and note that I've changed the legend scale from 0 to 1.6 Tesla. And we're going to look at particularly the outline associated with our magnet. And particularly we just concentrate on the greens here in the magnet region. There's a bit of dark green down the bottom right corner here. There's no dark green up in the top right. I've got a middle green color here. It's got a nice lobe of flux density. And I've got a lighter green here throughout. And then I've got lobes of yellow and light tan here on both of the corners up close to my rotor core. If I now switch and look at that same magnet at 77 degrees steady state, the bottom corner here where I had just a little bit of dark green has significantly expanded in dark green. I now have a lobe here of dark green on the top. My middle green color has expanded well beyond where it initially was. In fact, it's going through the entire thickness in the middle of the magnet. My lobes of this light green and yellow have expanded up and towards the corners to the point where in the bottom here, I have no longer any brown or light tan, and the light tan on the top is significantly reduced. So consistent with 57 degree temperature rise, I've lost flux. In fact, I've lost 6% of the flux, and that's very nicely depicted in this graph. So now if I scrutinize the overall values of flux in this magnet, and I look at the green shades and compare that with the legend, what I see is that the lowest values of flux are between 0.8 and 0.9 Tesla. And what this does is it gives me some confidence in what's going on. And number one, what it does is it tells me that there's no threat to demagnetization due to the temperature rise, because the flux density, that worst case scenario, are still significantly above the knee in the curve of the second quadrant for the magnets. So I don't have any threat of demagnetization. And the other thing to note is that although we have lost some flux density due to elevated temperatures, we do know that if we were to cool off the magnet, then the flux loss is reversible and the original flux levels would be returned to the magnets. one additional concern that we have is the integrity of the winding. And so we're going to assess first the resistance values, and then we'll look at some insulation type of scrutinies in a moment. But if we take the winding loss, we can take the winding loss and compute the line-to-line resistance in both cases, the 20-degree case and then our steady state case. So at 20 degrees C, we see here that our winding resistance line-to-line is 1.79 ohms, and at 95 degrees, it's 2.3 ohms. And if we do the math, that's a 30% increase, and that's indeed consistent with our 75-degree temperature rise. So now what do we do with that temperature? Well, we're going to look at and see how we would scrutinize the insulation lifetime. And this might include your slot liner. It might include the insulation around the conductors themselves and any epoxy that you might impregnate as you're creating the machine. I've included here a graph that I got from an IEEE source, and it depicts the winding temperature on the bottom and the lifetime expected of the insulation for 4 different classes of material, an A, a B, an F, and an H. And then I've overlaid on top of this graph a red line which indicates my 95 degrees of operational temperature for our winding. And if we look at the intersections of each of the classes, we will be able to look at and assess the potential lifetime for the insulation. So for Class A, the intersection occurs at around 35,000 hours. For Class B, it occurs at 230,000 hours. And for F and H, it's significantly above 1,000,000 hours. And what does this mean to us? Well, what this means is that for Class A, the insulation will have its integrity and respond reasonably for about 4 years. Class B will respond reasonably and have appropriate material properties for 26.3 years. And for classes F and H, which are above 1,000,000 hours, we have a cutoff of 114 years. So as we're assessing the nature of the components that we're putting in the machine and the insulation we're using, based on the intended lifetime of the motor, we can make choices. And so, for instance, if our machine is intended to have a warranty or a guarantee of 2 years lifetime, let's say, Class A would be suitable, and it would certainly work and be reasonable within that warranty. If your warranty is instead 25 years or 10 years or something in between, you definitely would need to jump up to Class B. And if you needed to ensure a permanent lifetime of the motor, you'd have to jump up to Class F and H. But knowing the temperature of the winding ahead of time allows you to make a cost-benefit assessment of what sort of insulation you need to put in. I'm pleased to pronounce that we have reached a design success. This is what it looks like to scale. And our design success is actually 20 million-Newton meters at 20,000 RPM. We achieve this with a 3-phase brushless permanent magnet motor. We achieve this with a 100% duty cycle and steady state operation for an hour. And we did this all within a package size, which is 25 millimeters diameter and 25 millimeters long. Thank you for your time.